Hello students, in the present video lecture, we'll discuss about organization of hardwired control as well as microprogrammed control unit. A complete processor. The design objective of any processor is to reduce number of clock cycles required in order to execute any instruction. Ideally, suppose the instructions are completed or any operations can be executed in one clock cycle. In one clock cycle, we can achieve better performance. So we considered single bus structure as well as multi-bus structure. However, in the case of single cycle processor, design is inefficient and difficult to implement since every instruction execution has to be completed in one clock cycle. So in the case of single cycle processor, each instruction need to be executed or completed in one clock cycle. The performance improvement can be achieved if fetch as well as execution phases. So we are having two phases while executing any instruction. The first one is fetch phase, the second one is execution phase. Suppose if you are overlapping these instructions, or if you are overlapped fetch as well as execution instructions, that instant we can achieve better performance. So this overlapping of fetch and execution phases is called as pipelining. Pipelining is a feature of all modern processor. Latest processor includes all instruction unit which fetches many instructions in advance and places them in a queue. Other enhancement includes having multiple functional units such as integer unit, floating point unit and instruction unit, which operates on respective type of data in parallel. A powerful processor can be designed using the structure by considering the cache, instruction cache as well as data cache. So the powerful processor consisting of separate cache structure in order to store the data as well as the instruction. The instruction cache is used in order to store the instructions and data cache is used in order to store the operand or else the data. Only if the information is not available in cache, then only the processor can access the memory. If the data or instruction, if it is not available within the cache, then only the processor will try to access the data from the main memory. This reduces the memory access time as well as it improves the performance. The processor is connected to the system bus and to the main memory by means of bus interface. So the processor is connected to the system bus. The processor is connected to the system bus and to the main memory by considering its bus interface. Using multiple units and pipelining, it is possible to design a powerful processors. The processor that executes the instruction at a rate exceeding 1 instructions per clock cycle. If the processor is able to execute one instruction, that means exceeding one instruction, that means more than one instruction per clock cycle. which is called as superscalar processes. Superscalar processes. To execute the instruction, the processor must generate control signals in a proper sequence. 7 non-overlapping time slots are required for executing the instruction. Each step is completed in one clock cycle. Hence, to ensure the proper operation of the processor, efficient design of control unit is very much necessary. So the control design or control signal design approaches into two categories. The first one is hardwired control. First one is hardwired control. The second approach is microprogrammed control. Microprogrammed control. So the required control informations are determined by the following informations. The first one is contents of control step control step counter. Second one is contents of instruction register. Third information is contents of condition code flags. Condition code flags. And the last one is external input signal. Such as MFC and interrupt request. So these are some set of informations that can be required in order to generate the control signals. So first we'll consider hardwired control. The control signals are generated using logic circuits such as gates, flip-flops as well as decoders. The control signals can be generated by considering some set of logic circuits such as decoders, gates and flip-flops. Decoder bar encoder block is a combinational circuit that generates required control output signals depending upon the state of all the inputs. So decoder bar encoder block, it checks the status of all the inputs and it will generate the respective control output. So next comes instruction decoder. It decodes the instruction decoder, which decodes the instructions loaded into IR. If IR is an 8-bit register, then instruction decoder generates 256 lines, one for each instruction. It consists of a separate output lines from instruction 1 INS1 to instruction M for each machine instruction. According to code in the IR, any one output line among instruction 1 to instruction yum can be selected and all other lines are set to 0. Out of these many set of instructions, any one instruction output line will be set to 1. So other instruction output line will be set to 0. So next block is step decoder, which provides a separate signal line for each step in the control sequence. So next is encoder block. It gets the input from instruction decoder, step decoder and external inputs and conditional codes. If it uses all these inputs to generate individual control signals like Y-in, PC out, add, end and so on. For example, if we want to generate one control signal Zin, so that is equal to T1 plus T6 dot AND plus T4 into branch instruction. This signal is asserted during the time slot T1 for all instructions, during T6 for an add instruction, during T4 for unconditional branch instruction. When run is equal to 1, counter is incremented by 1 at the end of every clock cycle. When run is equal to 0, counter stops counting the values. So now we'll consider advantages as well as disadvantages of hardwired control organization. So the major advantage is can operate at high speed, and the major disadvantages are since number of instructions per control lines is often in 100, the complexity will be more. The cost as well as difficult in design, which is very costly and difficult to design. The control unit is inflexible because it is difficult to change the design. The diagram shows hardwired control unit, so which consisting of decoder and encoder block, which is a combinational circuit that generates required control outputs depending upon the state of all the inputs. So here we can consider the input is from the control step counter, external inputs and condition codes. So next we'll consider a detailed block diagram while considering separate decoder or encoder block. Separation of the decoding and encoding functions. The step decoder provides a separate signal line for each step in the control sequence. So here we can observe that we are having one step decoder which provides a separate signal line for each step in the control sequence. The output of the instruction decoder consisting of output lines from instruction 1, instruction 2 till instruction yum. So out of these set of instructions, instruction 1 to yum, any one instruction line will be set to 1. So that will be set to 1. All instruction lines will be set to 0. The input signal to the encoder block are combined to generate individual control signals like, so we can consider different control signals like Zin, add, PC out, end, so on and so on. So in the diagram we can observe that instruction register which gives multiple inputs into the instruction decoder. So instruction decoder which will select any one instruction among m number of instructions, and the step decoder provides a separate signal line for each step in the control signals like T1, T2 till Tn, and the encoder also receives the inputs from the step counter, external inputs or condition codes. The required control signal can be determined by the content of step counter or control step counter, content of instruction register or IR, contents of condition code flags, as well as in external inputs. This may be either the external inputs in the sense memory function complete signal or any kind of interrupt signals. So by considering these inputs, these different inputs, the encoder block can generate the control signals. Either the control signal may be run or end or Z-in, add, PC out, etc. The diagram shows how we can generate the control signal end by considering the logic gates. So the second approach in order to generate the control signal is microprogrammed control unit. Microprogramming is a method of control unit design. The control signals are generated by a program similar to machine language program. So here in the case of microprogrammed control unit, the control signals can be generated by a program similar to machine language program. So here we can consider some parameters like control word and micro routine. So the meaning of control word or CW is a word whose individual bits represents various control signals. So control word is nothing but a word, but the single bit represents various control signals like add, PC in, end, Z-in, etc. Each of the control steps in a control sequence of an instruction defines a unique combination of zeros and ones in a control word. So basically the control word information will be in terms of patterns of zeros and ones. Individual control words in a micro routine are referred as micro instructions. Individual control word in micro routine is referred as micro instructions. A sequence of control words corresponding to control sequence of a machine instruction constitute a micro routine. So micro routine in the sense a sequence of control words corresponding to control sequence. The micro routine for all instructions in a instruction set of a computer are stored in the special memory called as control store. So we can store all the instructions or micro routines for all the instructions in an instruction set. For the given respective computer can be stored in a special memory segment called as control store. In short, we can call it as CS. Control unit generates control signals for any instruction by sequentially reading control words of corresponding micro routine from CS. The micro PC, that is MuPC, is used in order to read control words sequentially from the control store. Every time new instruction is loaded into IR, output of the starting address generator is loaded into micro PC. Then micro PC can be automatically incremented in order to fetch the next instruction from the control word or from the control store. The diagram shows basic organization of a microprogrammed control unit. A structure of the microprogrammed control unit consisting of starting address generator, instruction register, clock, microprogram counter, that is MUPC, followed by control store, that is MUCM. The control unit can generate control signals for any instruction by sequentially reading the control words of corresponding microroutine from the control store. So the control signals can be generated by reading the control words, of the corresponding microroutine from the control store. To read sequentially, we can make use of microprogram counter, that is MUPC. In order to read the content from control store, we can make use of MUPC. Every time a new instruction is loaded into IR, every time the new instruction can be loaded into IR, the output of the starting address generator is loaded into MUPC. So each time new instructions can be loaded, here new instructions can be loaded into IR, and the output of IR is connected to the starting address generator. So now the output of the starting address generator, which gives the input to the MUPC, then MUPC is automatically incremented for each successive instruction fetch. So here MUPC will be automatically incremented in order to fetch the next successive instruction. Hence, the control signals are delivered to various parts of the processor in the correct sequence. So the basic organization cannot handle unconditional or conditional branching. So the microprogrammed control unit, it cannot handle both conditional as well as unconditional branching. So we have to use branch micro instructions. So we have to use branch micro instructions. These micro instructions specify the branch instructions, branch address. So they can also indicate which external inputs, condition codes or bits of the IR should be checked as a condition for branching. So here we can observe that the micro routine for the instruction by considering conditional branching. So we can observe that the micro instructions with respect to different address is specified like PC out, MAR in, read, select for, add. So this is nothing but the actual instruction fetch phase. It's common for all the instructions. So next we considered if n is equal to 0, then branch to micro instruction 0, that is the starting address. Offset field of IR out, select Y, add Z in. And finally we can copy the value into PC in. Z out, that is the branch target address, will be copied into PC in. A micro instruction at location will be checked with respect to the value of n. If the bit n is set to 0, a branch takes place to the location 0 in order to fetch a new machine instruction. Otherwise, the next instruction at the location that is 26th location will be executed in order to put the branch target address into register Z. So if the condition n is equal to 1, go to 0, address 0, else it can execute the next instruction at location 26 in order to put the branch target address into the register Z. So the modified microprogrammed control unit is shown in the diagram. Starting and branch address generator block receives the input from external inputs as well as condition codes as well as from IR. So here we can observe that the starting and branch address generator receives the input from IR, external inputs as well as condition codes. In this control unit, the MuPC is incremented every time a new instruction is fetched from the control store. When a new instruction is loaded into IR, MuPC is loaded with the starting address of microroutine for the instruction. So whenever the new instruction is loaded into IR, MuPC will be loaded with the starting address of microroutine for the instruction. When a branch micro instruction is encountered and the branch condition is satisfied, the MuPC will be loaded with the branch address. So suppose if there is a branch instruction occurred, at that time the branch condition is also satisfied. So now the MuPC will be loaded with the branch address. When the end micro instruction is encountered, the MuPC is loaded with the address of the first control word in the microroutine in order to go to the fetch phase. So next we'll consider micro instructions. A simple way to structure micro instructions is to assign one bit position to each control signal required in the CPU. Suppose if there are 42 signals are available, then micro instructions will be having around 42 bits. The major drawbacks of microprogrammed control unit is assigning individual bits to each control signal results in long micro instructions because the number of required signals is usually large. Available bit space is poorly used because only a few bits are set to 1 and in the given micro instructions. So we can enable only one bit can be set to 1. The solution is the signals can be grouped because most signals are not needed simultaneously. Many signals are mutually exclusive. Consider difference between hardwired control and microprogrammed control unit. So we'll take different attributes. So first we'll consider definition. Hardwired control is a control mechanism to generate control signals by using gates, flip-flops, decoder and other digital circuits. Microprogrammed control is a control mechanism to generate control signals by using memory called as control store, which contains the control signals. So if we are considering speed as attribute, hardwired control which performs with better speed, but microprogrammed control unit which is slow. So next is control functions implemented in hardware. The control functions can be implemented in software with respect to microprogrammed control unit. So the hardwired control unit which is not flexible to accommodate new system specifications or new instructions. But in the case of microprogrammed control unit which is more flexible, so we can accommodate new system specifications or new instructions, redesign, if suppose we have to design it again. Ability to handle large or complex instruction set, difficult which is easier with respect to microprogrammed control unit. So ability to support operating system as well as other features, it's very difficult, but with respect to microprogrammed control which is easy. So the next attribute is design process which is complicated under hardwired control. So but in the case of microprogrammed control which is systematic. So next is application which can be used with respect to RISC microprocessor. So in the case of microprogrammed control unit, so we can consider mainframes as well as microprocessors. So next parameter is instruction set, usually under 100 instructions, usually over 100 instructions. So here the number of instructions which are limited within 100, but here microprogrammed control unit we can consider more than 100 instructions. ROM size, so in the case of microprogrammed control unit, the ROM size required around 2K to 10K by 20 to 400 bit micro instructions. Chip area efficiency, uses lesser amount of area, but in the case of microprogrammed control unit which uses more area. So here we can observe that in the case of hardwired control unit, so with respect to the state of the register, it can generate the control signals. So in the case of microprogrammed control unit, so it can generate the informations or control signals with respect to the control store. So it consisting of micro instruction register which will generate the control signals. Techniques of grouping of control signals. So we can group the control signals either in vertical organization or else with respect to horizontal organization. So in the case of vertical organization, many encoded schemes that use compact code to specify only a small number of control functions in each micro instructions are referred to as a vertical organization. The minimally encoded scheme in which many resources can be controlled within a single micro instruction is called as horizontal organization. Vertical organization which is slow, but horizontal organization which is useful when high operating speed is required. Vertical organization has short format, but horizontal organization has longer formats. The vertical organization gives limited ability to express parallel micro operations, but horizontal organization express ability to perform high degree of parallelism. Vertical organization which considers encoding of control information, but in the case of horizontal organization, little encoding of control information.